Hello, Cracking the Cryptic. I'd like to share with you today a coloring technique that I've developed for puzzles which contain lots of cells with two different possible values, even when those values aren't always in the same pairs. For my example, I'll be demonstrating on yesterday's puzzle, Tangled by DVFrank. I've started with Mark's progress at 14 minutes 40, when he says that he'd really like to color the 3s and 4s, but he's not sure he has enough of these 3-4 cells to do that. You can see here that we do have a few cells with two possible values. We have all these 1-2s that Mark has colored for us. We also have these 3 6s, 3 4s, 4 6s, and we might discover some more as we go further into the puzzle. Now for this technique, we will need two colors. In this case, Mark has already colored all the 1s and 2s in blue and orange, and this technique is completely compatible with that, so we'll build on that coloring. I'm going to start with these 3-4 cells in the corners here. 2-cell cages, like these 5s, are very convenient for this technique since one digit completely determines the other. In this case, each of these cages has to be a 2-3 cage or a 1-4 cage. The principle we're using here is going to revolve around keeping track of which cells being high makes which other cells low and vice versa. For example, in this case, if this is a 1, then it's its lower possible value. That makes this one a 4, which is its higher possible value. Similarly, if this is a 2, which is high, then this one has to be a 3, which is its low possible value. Since those are opposite, we are going to give this 3-4 the opposite color, like that. And because the puzzle is symmetrical, we can repeat that down here. The 1-2, if it's a 1, it has to go with a 4. If it's a 2, it has to go with a 3. That means that low goes with high and high goes with low. So we give this an orange color. The next place to look is this other 3-4 here. It's facing this 3-4 that we have just colored, which means it can't be the same value. If this one's a 4 high, then this one's a 3, which is low, and vice versa. So this one is going to be orange, and symmetrically, this one is going to be blue. Now right away, we can start reading off a result from our coloring here. We can see that this 3-4 cell and this 1-2 cell have to be opposite here. If this is a 2 high, then this one has to be a 3 low. And if this is a 1, then this is a 4. So they have to add to 5. Which means that the 12 cage has to have a 7 left over. And we can see that again down here. One of these has to be the opposite height from the other, which means 1, 4, or 2, 3, they have to add to 5. How do we know that? Well, the coloring encodes this whole chain of cells from this 1-2 to this one, to this one, down to this one, to this 3-4, to this 3-4, but we don't have to care about all of those intermediate cells because we just care that they alternate between high and low, which gives us that these two alternate. And this has to be a 7. Now for something a little more complicated, let's look at these 3-4, 3-6, and 4-6 along the edge here. Then you're going to have to make a triple, and each of them only has 2 possibilities, which means that the value of any one of them is going to tell us the other two. We might think we'd need 3 colors for 3 cells, but we're going to find that we only need 2 colors because we only need to distinguish 2 possibilities. Each cell will eventually be either high and low, and that'll tell us the other 2 cells, whether they're high or low. For example, here, this 3, 4 and this 3, 6, one of them is going to be a 3. And that will be the lower value for whichever cell it is. So if this one's low, this one can't be low. And vice versa, if this one's high, then this one has to be low. We'll give them opposite colors. Same thing again on 6s. If one of these is a 6 and it's high, then the other one has to be not a 6 and low. So we're going to give this one an opposite color. Now you'll see that that makes these two, the 3, 4 and the 4, 6, the same color. Is that a problem since they're the same color and they're in the same column? No, it's not a problem. Because if this one is a 3, then this one has to be a 4. Both of those are low. If this one's a 4, then this one has to be a 6. Both of those are high. So they should be the same color. As we extend that coloring over towards the other corner here, with orange here, alternating with blue here, we'll see that that lines up perfectly with the coloring that we already have in that corner. And that's always going to happen as long as we follow this rule, because the coloring encodes this whole chain of cells. We don't have to think about the intermediate cells because it'll keep the invariant and make sure that the parity is the same.